Hi guys, how's it going? I hope everyone's all right. I'm a little bit whispering here because my children are sleeping and I don't want to wake them up, but let's get into today's activity. So typically at this point in the school year, as we got through the fundamental forces, we would do this lab called car and ramp. I'll explain what it's about in a little bit. But it essentially goes over, it kind of combines Newton's three laws, especially the second one, force equals mass times acceleration. Here's a good example of how that is demonstrated. We did a couple of demonstrations in a video that I posted. Here's another really good one. We have this girl who has a smaller mass than this linebacker over here, and you can see that she is accelerated to a much greater degree than he is. I'm sorry if the screen capturing software that I'm using might have a little bit of a slow frame rate, so I don't know if you can see this really well, but I think you'll get the gist of it, that she goes absolutely flying, and he just kind of gets pushed back a little bit. So there's a little bit of F equals ma, there's a little bit of equal and opposite reactions that are going on here. This is another great one. So I think this is how all sports will be played going forward. This is safe from coronavirus. You're on your own little bubble. There's no way you're going to be sharing germs with anyone in here. I think it's a fantastic sport, and it also demonstrates Newton's laws very, very clearly. Boom! Look at that. That's just great. I love that every time. Okay, so let's get into the car and ramp lab. I really like this lab. This is actually probably my favorite lab of the whole year. Not because it's explosive or flashy. It's not like the DNA lab where you get to mix chemicals and you get this really cool product at the end of it. It's actually very, very simple. It's so simple that you can make a very clear prediction. You can understand the premise of it very clearly, and you can make a clear prediction from the onset. There's very little confusion about what's happening in the lab, which makes it great to grapple with and to think about as you're doing it. What I like about it is that it's for many students, I would say 90% of the students, this lab goes against what they think is going to happen. So you have this hypothesis, you have this prediction, and then the results of the lab tell you something totally different. And you have to think back about how you approach the lab, how you approach the premise, and be like, wait a minute, why is this not exactly happening how I thought it was going to happen? The data says something totally different. Now, unfortunately, you guys can't be there to produce the data. You won't. This is something that we'd have to do in class, and you won't be. It's not possible that we can be together and you can let the cars go down the ramp and collect the data and use the motion sensors. But that's okay, because in years past, I've collected plenty of data from my previous students, and we'll be able to use their data and analyze the results just as we would, which is really the most important part. Well, in this lab, there are two experiments that we'll be doing. The first is we're going to be changing the slope of a ramp and letting a car going down it, and the second one we would change the mass of the car as it goes down the ramp. Okay, so on Friday you did a couple of predictions. We'll get to those in a second. All right, the acceleration due to gravity is always 9.8 near the surface of our planet. That's a constant acceleration. The only thing that would change it is if you have a parachute or a big surface area to increase your wind resistance, your drag, as you fell through the atmosphere. But for the most part, solid objects are going to fall at a rate of 9.8 meters per second per second. So with this acceleration and the masses of these objects, we can calculate the greatest net force on these objects, or at least estimate them. So in this case, in our first scenario, we have a mass of 10 kilograms. The acceleration due to gravity is 9.8, but this mass is resting on a surface, which means that there's an equal force pushing it upwards, and it's not falling down. So our net force is 0. It's balanced, and there is no acceleration. Conversely, on the other end of this, we've got this 10 kilogram, same mass, same object, but there's no floor supporting it. So it's going to free fall, which means that there is a net force of 98 newtons going down on it. So in between, we have a range that goes from 0 to 98. And so we can kind of roughly estimate. We'd have to do a lot of trigonometry and some pretty complicated math to get the exact value, but we can estimate it that this is maybe about 65 newtons. And if this is 65 newtons and this is 98 newtons, this one must be somewhere in between those two. So let's say about 78 newtons. So in this case, when there's no supporting structure, we're going to have the greatest net force. And to summarize these trends, let's say that increasing the slope would result in a greater net force. So as we have a slope of 0, the net force is 0. As the slope increases, we get a stronger net force. As it increases even more, our net force increases. And if you have a completely vertical slope allowing the object to free fall, you will have the greatest net force possible. So that's basically what would happen in our first experiment. So this is what the setup would look like if we did it in class. We'd have the textbooks down here to stop the cart as it fell. We'd have a bunch of textbooks on this side to give a slope. And what you would do is change the number of books to change the slope of the plank. So you might start off with 4 textbooks, then increase up to 8, and then finally up to 12 to get your highest slope. And up at the top, you might see that familiar looking vernier motion sensor, and that's going to capture the acceleration of the cart as it goes down the ramp. So in this lab, the idea is the data that you'll be provided with, let's just pretend that we did the data, we did the lab, what you're going to see is the relationship between force and how increasing the force may directly impact acceleration. So in this lab, our independent variable, the thing that we're changing is the slope of the ramp, which is also the force. The dependent variable is going to be the acceleration of the cart, and the thing that we're not changing, the thing that's staying the same, is the mass of the car. So that's how experiment number 1 gets played out. In the previous exit ticket, I had you guys make some predictions about experiment 1. I said, if you change the slope of a ramp to make it steeper, what will happen to the net force acting on the cart? Well, about 71% of you said that it would increase, and then just over a quarter of you guys said that it would either decrease or stay the same. So hopefully the previous slides would have clarified what would have happened. And then I asked, if you change the slope of the ramp to make it steeper, what will happen to the acceleration of the cart? Well, hopefully if you increase the slope, if you increase the slope, you'll increase the force, and if you increase the force, you'll increase the acceleration. So that kind of makes sense. So a large percentage of you, a large majority of you, 86%, said that it would increase. So when you get the numbers in the handout in the document, you'll see if the numbers match your prediction. In the second experiment, which would usually happen on day 2, the thing that changes is not the slope, but the mass of the cart. So you would take washers or some masses, some kind of weights, and you would put them in the cart to make the cart heavier. So here we'd have our first example. We'd maybe have a cart with no mass in it, which on its own weighs 10 kilograms. Then we would add 10 kilograms for a total of 20, and we'd let it go down the ramp. Then we'd add some more and let it go down the ramp again. So again, in that previous exit ticket, you guys made some predictions. If you kept the slope the same, but you increase the mass, what happens to the net force acting on it? Well, there's a little bit less conviction that it would increase, and a few more of you said that it would decrease or stay the same. And in our last question, if you kept the slope the same but increase the mass, what happens to its acceleration? This one was, almost split evenly 3 ways. There's no clear majority. There's nothing that's happening here. I really like the outcome of this because this is the question that we're really going to see some interesting data that's going to be produced by exploring this question. So what's going to happen today for the rest of in today's class, I'm going to provide you the results of this lab had you done it like you would have in class, and then using that data, you'll see how does that match up with these predictions. How does it match up with these 4 questions? You'll graph that data, and that will give a clear presentation of what exactly is happening to the force and the acceleration of the cart as you increase the slope and increase the mass. Okay, so if you have any questions, let me know. Email me, put a comment in the Google Classroom, and I'll get back to that as soon as I possibly can. And good luck with this. It's a really interesting outcome. Some of you may get it, but we'll definitely go over the results of it as they come in tomorrow. Okay, thanks for watching, guys.